In our first problem here, H&R Block claims that the average taxpayer who files their own tax return spends a mean time of 22.4 hours preparing their return. The IRS claims that the average time is not that long. So the claim is it's not that long. So that'd be the same as saying it's shorter. If you want to do a hypothesis test to support the IRS claim, at the time is shorter, what will your null and alternative hypotheses be? So H0 and HA we need. So start with HA, which is what you're trying to show. So you're trying to show the time is not the 22.4 hours. And then this will be a mean. This is a hypothesis test of the mean because you would measure mean time, not proportion. So mean less than 22.4 would be your alternative. And if that's not the case, then your mean would equal 22.4. So there's no alternative. Describe a type 1 and type 2 error. So type 1, remember, is when you reject the null when it's really true. So you're going to reject that the mean is 22.4, you're going to conclude that it's less than 22.4. So you're going to conclude that the mean is less than 22.4 hours when it's really not. And then type 2 is when you accept the null even though it's false. So in that case, you're going to conclude that the mean does equal 22.4 when in fact the mean is actually less than 22.4. So null alternative and then type 1, type 2, I will have you do those as Canvas problems. And number 2 here, we have a random sample of 75 participants. That's going to be our sample size. So n is equal to 75. In the Boston Marathon, they had a mean completion time of 2.74 hours. With a standard deviation of 0.62. So the 75 participants, that's going to be a sample. So the mean of 2.74 is going to be an X bar sample mean. And then the standard deviation, 0.62, is going to be S. That's sample standard deviation. We're going to do a hypothesis test here at the alpha is 0.10 level. To decide if the mean completion time for all participants is different from last year, which had a mean time of 2.56, and then interpret our results. So step 1 here, we need our null alternative hypothesis. So H0HA. So we're trying to decide here if the mean completion time is different. That's a two-tailed test. So that's going to be mean not equal to, and we're testing against last year's value of 2.56 hours. How anyone runs 26 miles in, some guys around 2 hours is beyond me. It's like 5-minute miles for 26 miles. I can't run one 5-minute mile. And then your null hypothesis here is going to be that the mean does equal 2.56. So those are opposites of each other. Step 2, you are going to determine your alpha. In this case, it is given. Alpha is 0.10. So that's probability of a type 1 error. Step 3, we are going to sketch our rejection region here. So this is a two-tailed test. So we've got our t-distribution. Going to use a t-distribution here because our population standard deviation is unknown. We're given s, not sigma. And in the middle here we have t equals 0, and we're doing the test at a 0.10 level. So that means here that our alpha over 2 is going to be half of 0.10, so 0.05. And two-tailed tests, we're going to have two rejection regions. So we're going to have a rejection region over here. This is 0.05. And then we're going to have a rejection region on the left also, because it's an equal, not equal test. And that area is also 0.05. So, and then this value down here, that's going to be the t-value with area 0.05 to the right. And so to get that t-value, we're going to do inverse t. And then we need to put in the left area, which is 0.95. So if 5% is to the right, this area is 5%, then 95% is to the left. We want the left area. And then the degrees of freedom, which are 1 less than the sample size. So 74. And pull up the calculator. And so we'll go to the distribution menu, second variables. We want inverse t, which is number 4. Our area is 0.95. And degrees of freedom, 74. Already set there. 1.6657, so 1.67. And then over here, this will be negative 1.67. So if our test statistic is bigger than positive 1.67 or less than negative, then we will reject the null hypothesis. So, and then step 4, we calculate our test statistic. So t-test is our sample mean, x bar, minus the hypothesized mean. And then we divide by the standard deviation of the sampling distribution. So that's s over square root of n. So our sample mean was 2.74 minus our hypothesized mean, last year's race, 2.56. And then we divide by s was 0.62, and then over square root of 75. And then if you plug that into the calculator, you will get negative 2.51. So you can double check me on that. And so that negative 2.51, that's out here. So it'd be about right here. So our t-test is negative 2.51. It is in the rejection region, so step 5 here. So our t-test, which is negative 2.51, is less than negative 1.67, which is our critical value. So this is going to tell us that we need to reject the null hypothesis. Reject H0. And then step 6 is to interpret our conclusion. So this always refers to the alternative hypothesis. Either there is or there is not sufficient evidence. So here we rejected H0, so there is sufficient evidence to conclude that the mean time is different. To conclude mu is not equal to 2.56. So the mean time differs from last year, which is the 2.56. So, and then if I have you do this in the written portion, then I want you to write out the 6 steps. If I have you do it as a Canvas, then I'll take you through the 6 steps and you'll have to fill in the blanks with the drop downs. Next up here, in a hypothesis test with mu equal 15 and alternative mu greater than 15, a sample of 81 observations. That's our sample size here, so n is equal to 81. Gave a sample mean of 15.4, so x bar is 15.4. With a standard deviation of 1.8, so S is 1.8. Find and interpret the p-value. Include comments on the role of different alpha values in your discussion. Okay, so remember that the p-value is the area past the test statistic. So if we were to sketch our distribution here, it's our t distribution, and we're testing mu equal 15 against mu greater than 15, so it's an upper tail test. So we are going to have our rejection region on the right. So this is going to be our test statistic, so we want to put our t-test in there. And then our alpha value here would be, well, it'd have to be bigger than the p-value. So our p-value is this area right here past the test statistic. It'd have to be bigger than our p-value in order to reject the null hypothesis. So let's figure out that test statistic. So t-test here is again x bar minus mu 0 divided by s over root n. So our x bar value is the 15.4. We are testing against the 15 from the null hypothesis. Divide that difference by our s was 1.8. And then over square root of n was 81. So that'll actually be 9 in the denominator. And then if you plug this into the calculator, you will get 2.0 to the nearest tenth here. Actually, I believe it's 2.00. So our test statistic there is 2, actually ends up being 2 on the dot. So the p-value is the area past the test statistic. So we're going to use cumulative t-distribution, TCDF. And our lower cutoff is going to be 2. Our upper cutoff is infinity. We'll use 10,000. And then you need your degrees of freedom, which are 1 less than sample size. So that'll be 80. And let's compute that in the calculator. So we want to go to the distribution menu, TCDF number 6. So lower cutoff was 2, even, upper cutoff 10,000, degrees of freedom 80. And that value is 0.0244 to 4 decimal places. Usually do those to 4 decimals. And what this is this is the measurement of how extreme our test statistic is here. So how extreme is our sample data? And what we notice is that this is less than 0.05. Remember that the p-value can also be interpreted as the smallest alpha to reject the null hypothesis. So here, if our p, which is equal to 0.0244, if that's less than alpha, then that tells us that we will reject the null hypothesis. And if our p here, which is 0.0244, is greater than alpha, then we don't reject. So in other words here, if alpha is greater than 0.0244, we will reject the null hypothesis. If it's less than, then we do not reject. And then the other interpretation of p-value, remember this is measuring how extreme the sample is. So this is 244 tenths, hundreds, thousandths, 10,000ths. So also we could say 244 of 10,000 samples are as or more extreme than our sample. So those are two interpretations of the p-value. You can do it in terms of alpha here, but you can also interpret it as how extreme your sample is. All right, number 4, we've got some lead levels that we're testing here. Lead's hazardous, especially in children. CDC has determined that lead levels of 0.125 milligrams per kilogram can cause brain damage. So that's what we're going to test against. That's our reference level here. Random sample of 16 children, so that's our sample size, n equals 16. From Kankakee had a mean lead level of 0.117 milligrams per kilogram. And that's a mean, so it's going to be sample mean. X bar is 0.117. And a standard deviation of 0.013 milligrams per kilogram. So that's going to be S is 0.013. And then use a hypothesis test at alpha is 0.05. To determine if the mean lead level in children in Kankakee is below the danger level. So step 1, we need our null alternative, H0HA. So the keyword there, below, so if the mean is below, that'll be mu less than, and we're testing against the 0.125. If that's not the case, then the mean will equal 0.125. So there's our H0HA. Step 2, choose our alpha. That was given to us as 0.05. Step 3, sketch our rejection region. So this is a lower tail test because mu less than. So here's our distribution. We are going to have a rejection region on the left here. So reject H0 there. And this area right here is 0.05. So this value is going to be T 0.05 and then do the negative. So we need to find that T 0.05. So we're going to do inverse T. And the right area is 0.05, so the left area is 0.95. And then our degrees of freedom, 1 less than sample size, so 15. So let's go ahead and compute that. So second variables, inverse T is number 4. Our left area, 0.95, degrees of freedom, 15. Paste it, 1.75. So that means that this value here is negative 1.75. And then step number 4 is to compute our test statistic. So our t-test here. And again, we're using t-distribution because we're given sample mean, not population. That's the only way that we did it. So our test statistic here is again going to be x bar minus our hypothesized mean, and then divide by s over square root of n. So our sample mean there was the 0.117. Hypothesized mean 0.125. So the 117 is less than the 0.125, but is that just enough by chance, or is there actually something going on? Then our S here was 0.013. and then divide by square root of n, so root 16 would be divided by 4. So if we plug that into the calculator, we will get negative 2.46. So negative 1.75 here, so a negative 2.46 would be out here. So our t-test is negative 2.46. That is in the rejection region. So step 5, our t-test, which is negative 2.46, is indeed less than negative 1.75. So that tells us reject H0. And then step 6, state our conclusion. So it's always going to be in reference to the alternative hypotheses, which is mu less than 0.125. So that means you're below the danger level. So there is sufficient evidence to conclude that the mean lead level in Kankakee is less than the danger level. So it's not due to chance, even though it's a very small sample. And then problem number 5 here, we've got a random sample of 200 observations. That's going to be our n. So n is 200. Is selected from a binomial population of over 10,000. And the computed value of p hat is 0.32. So instead of giving us successes, they're giving us p hat. So p hat, which is x over n, is equal to 0.32. And then we're testing p equals 0.4 against p less than 0.4 at the alpha equal 0.10 level. So here we're dealing with binomial population, success or failure. So this is a test of proportion. So we're going to use the z variable here. So step 1, state our null alternative. Those are given to us. H0 is that the population proportion is less than 0.4. And then HA is, equal 0.4. And then HA is less than 0.4. Your equal is always part of the null. Step 2, select our alpha. That's given to us as 0.10. Step 3, sketch your rejection region if we're doing a classical hypothesis test. So here's our z distribution. This is a lower tail test, so our rejection region is going to be on the left here. And then this area here is equal to 0.10. So then our z down here, so z 0.10 would be for right tail. This is negative z 0.10. So let's figure z 0.10. So that would be 10% area on the right. So the left area is 90%. So remember, use inverse norm to do this one because it's z. And the left area is 0.9. And then we're dealing with z-scores here. So that's actually all that we need is inverse norm 0.9. Or you can also get that from the table of common rejection regions, and that is actually 1.28. So this z value is negative 1.28. So either inverse norm or the table. Now, if it's something other than alpha is 0.10, 0.05, or 0.01, then you have to do inverse norm to get your critical values. Step 4, we need our test statistic. So our z-test here. Remember that formula. You take your p-hat and subtract off p0, and then you divide by the standard deviation of the sampling distribution, which is the square root of p0, 1 minus p0 over n. So our p-hat was the 0.32. Our p0 that we're testing against from the null hypothesis, 0.4. And then in the denominator, since we accept that 0.4 is true unless proven otherwise, we're going to keep that in our standard deviation here. So 0.4, 1 minus 0.4, and we are dividing by, n was 200. And if you compute that in the calculator, you will get negative 2.31. So I'll let you double check that. That is out here. So negative 2.31, which is our z-test, test statistic. That is indeed in the rejection region. So step 5, our z-test, which is negative 2.31, is indeed less than negative 1.28, so quite a bit less than. So we're going to reject the null hypothesis again. So this is not due to chance. And there is sufficient evidence. So if you reject, there is sufficient evidence. So there is sufficient evidence. And it's always evidence for or not for the alternative. So there is sufficient evidence to conclude that p is less than 0.4. So 0.32 with a sample size of 200 was enough so that it was not due to chance. Now, let me say a little something here about, actually back up a little bit. Let me say a little something on this one, especially about test requirements. So notice it didn't ask for test requirements here. If you needed to do test requirements, remember that you need, so just a little note here, test requirements. So first, remember you need a random sample. And we were given that here. So that checks out. And then 2, you need NP0, which in our case is 200 times P0 is the 0.4. So 100 times 0.4 would be 40, and so 200 times 0.4 is 80, and that is greater than or equal 15. And then n times 1 minus p0. So that's going to be 200 times 1 minus 0.4, 0.6. So that will be 120. And both of those are greater than or equal 15. So if you need test requirements, you will have to check those two conditions. And then actually remember the test requirement for test of the mean. So your requirements here One, you need random sample. And we've got that right here. And then the second requirement is n greater than or equal 30 or a normal population. Our n was 16, which is less than 30. So n equals 16 is less than 30, but we're assuming a normal population with no outliers. So we've got normal population. So that would be test requirements there. And number 6, EPA tests independent random water samples. So we got random samples. They're independent for levels of the pesticide DST before and after a new city water filtration process. The first sample of size 40, so that's saying N1 is equal to 40, had a mean DST level of 31.4 parts per billion. So that would be X1 bar is 31.4. And a standard deviation of 4.5. So that's going to be S1 is 4.5. The second sample is size 50. So N2 is equal to 50. Had a mean of 29.9. So that's going to be our X2 bar. And a standard deviation of 3.7. So that's going to be S2 is 3.7. We're going to use a hypothesis test at alpha is 0.05 to determine if the treatment works. So if the treatment works, it should lower the lead level. So we can see that this is the before data and the after data. So before it was 31.4, after it's 29.9. So it should lower the pesticide level, excuse me. So this did lower it from 31.4 to 29.9, but not very much. So we don't know if that's statistically significant. So that's what we need to determine. So step 1 is H0 and HA. And actually, let's talk about test requirements on this one also, just in case I ask. So always at first random samples. So we got random samples is given. So random samples from the target populations. And then in this case, our sample sizes are 40 and 50, which are both greater than or equal 30. So this is a large sample test. So N1 and N2 greater than or equal to 30. That ensures that the sampling distribution for the difference of means is normally distributed. So our alternative, we're trying to show that this works. So that would mean that the second population mean is lower. So that would be mu1 is greater than mu2. And if that's not the case, then the two means would be equal. So if nothing happens, there's no change in the mean. And then second, you want to choose your alpha. Ours is already given, 0.05. Step 3, you want to sketch your rejection regions. So here is the sampling distribution for the difference of means. So greater than, so this is an upper tail test. So we've got a rejection region on the right. So reject H0 there. This area right here of this little sliver is 0.05. So then we need the z-value here. Z because this is large sample test. They're both greater than or equal to 30. So the z-value with 0.05 area to the right. That's 95% area to the left. And if you look in the table of common rejection regions, that's the 1.645. Step 4, we compute our test statistic. So our z-test here is going to equal the difference of the sample means. So x1 minus x2 on top, and there's no common difference we're testing against. And then in the denominator, our standard deviation we're approximating by s1 squared over n1 plus s2 squared over n2. So our first sample mean was the 31.4 minus the second is the 29.9. We're going to divide by, our S1 was 4.5, so 4.5 squared over that sample size of 40. And then plus the second standard deviation, 3.7. So 3.7 squared and divide by sample size of 50. And then if you plug that into the calculator, you will get 1.70 to 2 decimal places. And then step 5, that 1.70 is right here. It is just bigger than the 1.645. So there's our z-test is 1.70. And so our z-test, which is 1.70, is greater than the critical value 1.645. So that tells us reject the null. And then we state our conclusion. So we're rejecting. So there is sufficient evidence to conclude the alternative hypothesis is true. So mean 1 greater than mean 2. So that would mean that the treatment works. So parenthetically, mean 1 greater than mean 2. But in practical terms, that's what it means for the treatment to work. And then problem number 7 here, independent random samples are selected from 2 large normal populations with no outliers. So this is an independent sample test. We've got normal populations with no outliers. That's one of our test requirements. Our results are summarized in this table. We want a 90% confidence interval for the difference in means. So our confidence interval test requirements here so if I ask for them, first of all, of course, independent random samples. And that's given. Second requirement is that both populations approximately normal. So populations approximately normal. And that was given here. And then the third requirement is that the 2 variances should be equal. So the variance of the first population, sigma 1 squared, should be equal to the variance of the second population, sigma 2 squared. which we would call sigma squared. So that we would have to assume. Now, if they're not equal, that does kind of throw a wrench in the works here. But our sample standard deviations were pretty close, and those are estimators of sigma 1 and sigma 2. So first of all, we want to list our degrees of freedom here for the test, which is going to be n1 plus n2 divided by, or I'm sorry, subtract 2. So 12 plus 13 minus 2, which is 23. And then our alpha here is equal to 0.10 because 90% confidence, so that's 10% left over. And then for these are small samples here, so we're going to need our pooled estimator, SP squared. So that's our pooled estimator of the variance here. And remember that is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared. And then we divide by the degrees of freedom, the n1 plus n2 minus 2. So again, we're using that pooled estimator because n1 and n2 here are less than 30. That's when you use the pooled estimator. And then our confidence interval here is going to be x1 bar minus x2 bar. And then we do plus or minus. And then we're going to use t-values because small samples and standard deviation unknown. So it's be t alpha over 2 and then square root the sp squared, so our pooled estimator of variance, times 1 over n1 plus 1 over n2. So we've got everything except our t value and our sp squared. So since alpha is 0.10, that means alpha over 2 is going to be 0.05. So that means that we need t 0.05 to go in here. So that's going to be inverse t. 0.05 is the right area, and inverse t we use the left area, 95% left. And then our degrees of freedom, which are the 23. Let's go ahead and figure that. So second variables, inverse t, number 4. Area is 0.95 again, and then our degrees of freedom, 23. So 1.7138. Let's go ahead and use the 1.71. And then let's compute our pooled estimator. So n1 minus 1, so n1 is 12, so subtract 1, that'll be 11, times s1 squared, so 2.2 squared, plus 1 less than 13 here is 12, times 3 squared, and then we are going to divide by the 23 right here, degrees of freedom. So if you put that in the calculator, you will get approximately 7.01. So now we've got all the ingredients here. So our x1 bar, that was 20.5, minus x2 bar is the 18.3, and then plus or minus our t value 1.71, and then this will be square root our sp squared 7.01, and then times 1 over 12 plus 1 over 13. So that difference is 2.2 of the means. And then this entire difference here, plug that into the calculator, you will get 1.81. So 2.2 plus or minus 1.81. So 2.2 minus 1.81 is 0.39. And then 2.2 plus 1.81 is 4.01. So notice that this interval does not include 0, and that is a 90% confidence interval. So 90% of samples should give an interval that contains the population mean difference. And this does not contain 0, and that's one of the 90%. So that's telling us, if we wanted to make a decision, that there's pretty good evidence here that the population means here are actually not equal. Okay, so just to note it, the problem didn't ask this, but note that 0 here is less than the entire interval, 0.39 to 4.01. And that's where the population mean difference should be. So in other words, your mu1 minus mu2 that you're trying to estimate, 90% of the time should be in that interval. And that interval is greater than 0, so this is, with 90% confidence, evidence that the difference in the two population means, mu1 minus mu2, is actually greater than 0. Now we don't know what that means in the context of the problem, because here we're just given numbers. We're not told what the numbers mean, what they represent. And then the last question here, surveys conducted to compare the proportions here, not means, proportion of cancer survivors for two different treatments, A and B, two independent random samples of size 100. So N1 equals N2 equals 100. Are taken from each of the two populations. There were 36 survivors for treatment A. So let's let A be treatment 1. So that's actually not N1, that's X1. So X1 is 36. Survivor is going to be a success here. And then X2, 24 in group B. So X2 is 24. And then we're using a 99% confidence interval to make an inference. So here they're actually asking us to make an inference, like I did in the last question, about the difference in population proportions, P1 minus P2. Okay, so we need P1 hat, which is going to be X1 over N1. And then we need P2 hat, which is going to be X2 over N2. Oh, and let's just mention the requirements here in case I have you check them. So for proportion, we need independent random samples. That was given. Secondly, we need N1, P1, or in this case, P1 hat, to be greater than or equal 15. So N1 is 100. And then times our P1 hat, well, it's just going to give X1, which is 36. But let's see, 36 here, 36 over 100 is 0.36. And then this one will be 24 over 100, 0.24. So N1 P1 hat, so 100 times 0.36 is 36, and that's greater than or equal 15. And then we also need N1 times 1 minus P1 hat. So 100 times 1 minus 0.36, which would be 0.64, and that's 64, which is greater than or equal 15. And then same thing for P2, for population 2. So N2 P2 hat, which will be 100 times the 0.24, which is 24, and that's greater than or equal 15. And then N2 times 1 minus P2 hat will be 100 minus 24, which is 76, and that's greater than or equal 15. So that's your second condition. And then, or I'm sorry, that's actually the third condition. The second condition, just do these out of order, is that each sample is less than 5% of the population. So the sample here, so we need N1, comma, N2 less than 5% of the population. And that's certainly going to be true. Proportion of cancer survivors. I mean, there's millions of cancer survivors. And then let's go ahead and write out our formula for the interval here. So that's going to be P1 hat minus P2 hat is our point estimate, plus or minus. And then with proportions, you always use a z interval. So this is z alpha over 2. And then times our standard deviation of the sampling distribution for difference in proportions, which is going to be P1 hat times 1 minus P1 hat over N1. And then the same thing for N2, for population 2. So P2 hat, 1 minus P2 hat over N2. So P1 hat, 0.36, minus P2 hat, 0.24, plus or minus. And then this is 99% confidence. That means alpha is 0.01. So that means that alpha over 2 is 0.005. So that means that we need z 0.005. So 0.005 is the right area and 995 is the left area. That is also one of the table values for, you look at the table for the confidence coefficients for common alpha values for confidence intervals, and that's 2.575. You could also do inverse norm of 0.995. So 2.575. And then our standard deviation here, P1 hat, 0.36, times 1 minus 0.36 is 0.64. Divide by 100. Plus P2 hat was 0.24. 1 minus 0.24 is 0.76. And that's divided by 100. And then that difference there is 0.12. And then this will be plus or minus. And then this whole quantity, if you compute that in the calculator, you'll get 0.165. So 0.12 plus or minus 0.165. And that will give you the interval negative 0.045 up to positive 0.285. So now we want to make an inference. So our inference is going to be, well, are the two population proportions the same or are they different? Well, notice that the interval contains 0. Okay, this contains 0. And when it contains 0, that's when you do not reject the null hypothesis. That means that there is not sufficient evidence to conclude that P1 is not equal to P2. So if this whole interval was greater than 0, we would conclude that the difference here is greater than 0, so P1 greater than P2. If this whole interval was less than 0, we conclude that P1 minus P2 was less than 0. Here we're concluding that they're either equal 0 or not equal 0. So in this case, we would say practically the treatments do not differ. There's not a significant difference. So treatments don't differ in proportion of survivors. And that's important to know. So that's conclusion from a confidence interval. So you reject the null hypothesis if the interval does not contain 0. You do not reject if the interval does contain 0.